Good afternoon, and welcome to the Mirzakhani lecture. I am Brian Akra, and I'm president of the AMS, and it's my pleasure to introduce this very special lecture. The Mirzakhani lecture was established in 2018 to recognize the extraordinary achievements of Maryam Mirzakhani. Her career was extraordinary at every step, starting with her record as the first Iranian to win 2 gold medals in the International Olympiad, followed by an amazing doctoral thesis at Harvard University, the awarding of a Clay Research Fellowship, and then tenure at Stanford University. And alas, her life was tragically cut short by illness, but her impact on the career, on the field and the career of many people has been huge in geometry, in dynamical systems, and more broadly. We will see some of that legacy today because we're lucky enough to have Alex Wright, who worked with Maryam, to give us this lecture. Alex is currently an associate professor at the University of Michigan, and he also is a Clay Fellow, following in Maryam's footsteps. He has won numerous awards, including the Conant Prize of the AMS, a Sloan Research Fellowship, an NSF Career Award. And without further ado, let me turn it over to Alex.
Thank you for the kind introduction. It's an honor to be here today. I'm going to give what's at least half of the talk will be expository, but near the end I will talk about some joint work with Francisco Arana Herrera, who surely would have been a Mirzakhani student at Stanford if Mirzakhani hadn't passed away. He's now on the tenure-track job market. So this is a picture of Maryam Mirzakhani in her office, where I spent a lot of time with her as her postdoc, and I'm particularly pleased to be giving this talk in honor of her today. So the talk will be in 3 parts. Sorry, just a sec. And in the first part, I'm going to give background on Teichmüller spaces and curve graphs and the remarkable story that connects them. So all of the objects in this talk will have to do with surfaces. So specifically finite type surfaces. So you should think of a surface of genus G with some number n of punctures. At the bottom, I've illustrated a surface of genus 2 with 1 puncture that's sort of been pulled off to infinity. I'm going to start with the Teichmüller space of the surface, so T sigma or TGN, depending on what notation is convenient. This is the space of hyperbolic metrics on the surface up to isotopy. So as you probably know, a sphere has a unique evenly curved metric up to scaling, which is the usual round shape, and it's positively curved. The surfaces I will consider instead have many evenly curved metrics that look like a saddle at every point. They're negatively curved, and this is the space of all of them. And one of the most remarkable miracles that one learns early on in the story of complex analysis and geometry is the coincidence in complex dimension 1 between hyperbolic metrics and Riemann surface structures. So this turns out to also be the space of Riemann surface structures on the surface up to isotopy. A Riemann surface structure is just the structure of a complex manifold of dimension 1. So an atlas of charts to C whose transition functions are biholomorphisms. And I didn't write it out in detail, but I want to highlight now that these hyperbolic metrics are complete. So when there's a puncture of the surface, the metric has a cusp. So the puncture sort of is at infinity. So one of the most basic facts is that Teichmüller space is homeomorphic to a Euclidean space of real dimension 6G minus 6 plus 2n. And this will arise later. We have these finally many real coordinates for the space. And it's somewhat deceptive in terms of geometry, Teichmüller space is not a Euclidean space, and these coordinates are of limited usefulness. And the mapping class group, which is a countably infinite group of symmetries of the surface, acts on Teichmüller space, and the quotient is the moduli space of hyperbolic metrics, and this coincides with the moduli space of algebraic curves, of smooth algebraic curves over C. So when thinking about Teichmüller space, the first comparison or analogy one makes is to a symmetric space, like hyperbolic space or another symmetric space. And there's a very profitable analogy where you take facts known about symmetric space and try to figure out to what extent they will hold for Teichmüller space. But it's worth noting that actually Teichmüller space is as asymmetric as possible. So a symmetric space, you think of like this field of wheat. It looks the same at every point. If you're dropped off, it doesn't matter if you were from there, you have no idea where you are. Every point looks just like the other. And in comparison, you see a city. If you know the city, you're dropped off, you know exactly where you are, even if you can have poor eyesight and can only see a little bit around you. So actually, moduli space is like the city. And if you're put a little guy down on moduli space who's been there before, they'll know exactly where they are because each point in terms of the metric geometry looks different from every point. So you compare to a symmetric space, but it's much more complicated, and actually it's completely asymmetric. Now in understanding these moduli spaces and hyperbolic metrics, one of the first questions that arise is if the hyperbolic metrics can degenerate, and if so, how? And they can degenerate in a simple way, and that's that a curve, a geodesic, can get short. And you don't have to know any hyperbolic geometry for this talk, but there's one very, very important fact that you should keep in mind, which is that as a hyperbolic surface develops a short curve, it also develops a long collar around it, an embedded annulus. And in particular, this means you can't have two short curves that intersect, because when you have one short curve, it has this big collar, and then anything crossing it has to be long. Okay? And actually, as you pinch a curve, say this curve alpha in the middle on the slide, in the limit, what you get is two cusps. So you sort of pinched it and then maybe removed that pinch point, and it looks like a surface with two cusps. So here you have points of the Teichmüller space of genus 2 surfaces that, as you're pinching this curve alpha, are in a sense converging to a point in T11 cross T11, which is the Teichmüller space of genus 1 surfaces with one cusp cross itself. And this will play an important role in the talk. It's profitable to add points like these to Teichmüller space where you've pinched curves. And when you do, you get something called augmented Teichmüller space that I'll just denote TGN bar. A less common but more descriptive name for augmented Teichmüller space is the Deligne-Mumford boardification. So this is a partial compactification. You've added some points at infinity, but not enough to compactify Teichmüller space. But when you quotient by the mapping class group, you get the famous Deligne-Mumford compactification, MGN bar. And augmented Teichmüller space, as is alluded to on the previous slide, is stratified into pieces. So it's just made of disjoint pieces where each piece is indexed by a collection of disjoint curves that get pinched. And each piece is a product of smaller Teichmüller spaces. So on the last slide, you saw the stratum you get when you pinch alpha, and it's T11 cross T11. And in particular, for each simple closed curve alpha, you get a codimension 1 stratum where you pinch alpha. You can consider the closure of that stratum, which is everything you can get by pinching alpha and possibly some other disjoint curves. And you can readily verify with the collar lemma that the closure of the stratum of alpha intersects the closure of the stratum of beta if and only if they're disjoint. If they intersect, the collar lemma says when you pinch one, the other gets long. But if they're disjoint, you can pinch them both at the same time. So considering the combinatorics of this, you start to think about simple closed curves. Simple means they don't intersect themselves, and when they're disjoint from each other. And there's a useful object which encodes this combinatorics called the curve graph, C sigma. And it has a vertex for each simple closed curve up to isotopy, and you put an edge between disjoint curves. So on the left, I've drawn a genus 2 surface with 3 curves in blue, green, and red. And on the right, you see a small piece of the curve graph with a vertex for each of those curves. And red is disjoint from green and blue. But green and blue are not joined by an edge because they're not disjoint, not even after isotoping them. Any questions so far? Okay, so the basic facts about this graph, the curve graph is locally infinite because each curve is disjoint from infinitely many other curves. So it's a very big graph. It's connected. That's not super obvious, but you could take it as an exercise to do in your hotel room. Not super, super deep, but too hard to be an exercise is that it's infinite diameter. So this graph is big in every sense. It's locally huge, and it's actually globally infinite diameter as well. And to connect this to another word you might have heard, the curve complex, if you fill in triangles with this graph with 2 simplices and then fill in tetrahedra, et cetera, so you take the flag simplicial complex, that's called the curve complex. And to flip it around, the one skeleton of the curve complex is the curve graph. And for things of a more algebraic topology nature, it's very often important to work with the curve complex. Today I'm going to do geometry, so I might as well work with just the curve graph. Okay, so I want to give you a little history of this. So pre-1999, there was comparatively little work on the curve graph. So in '86, Harvey used it to show that the cohomology of the mapping class group has a version of Poincare duality. And in 1997, Ivanov used it to give a new proof of the result I alluded to before, that moduli space is as asymmetric as possible. Really, the modern era began in 1999, and I would call this the era of the Maser-Minsky machine. And before I tell you what it is, I'll tell you some of the motivation. So first of all, there is a feeling that Teichmüller space has some negatively curved behavior with the Teichmüller metric. And actually, it was very briefly a theorem that Teichmüller space is negatively curved before a mistake was found in the theorem. And actually, Maser put the nail in the coffin and gave an example to very clearly show that there's some positive curvature behavior as well. But still, there's the feeling that the negative curvature sort of rules the day in the end. And Maser wanted to ignore the positive curvature and really see the prevalent negative curvature, inspired by things like relative hyperbolicity. And he had in mind also what you might call word processing applications, so algorithmic problems in the mapping class group. Minsky's motivation was to prove one of Thurston's big conjectures on hyperbolic 3 manifolds, the ending lamination conjecture. And he went on to do that. So they provided a number of results that were very groundbreaking at the time and whose subsequent importance can't be overstated. The first of these results is that the curve graph is Gromov hyperbolic. So let me tell you what it means for a graph to be Gromov hyperbolic. It means there exists a delta, and then you say it's delta hyperbolic, such that all geodesic triangles are delta thin. So what's a geodesic triangle? Well, this is just a graph. So you pick 3 vertices and join them by minimal length paths, the paths with a minimal number of edges. And this is a geodesic triangle. And you require that each point on any edge is within delta of one of the other edges. So the triangles sort of bend in towards the center, and the different edges stay close to each other. So if you haven't seen this before, Euclidean space is not Gromov hyperbolic. So this will seem like a strange thing. And what you should compare it to is a tree. So we all know the simplest graphs are the graphs without cycles, trees. And so on the right, I've drawn a tree and I've drawn a geodesic triangle. So 3 points and the geodesics between them. And you can see that actually every point on any one of the edges is literally on one of the other 2 ledges. So actually, trees are 0 hyperbolic. And you should think of being Gromov hyperbolic as meaning that the space is tree-like for some purposes. And this is a very, very powerful notion. So I just want to have a little aside now. It's an ongoing topic of research what the best delta is. And I just wanted to illustrate this slide by 2 undergrads who had hoped to come to the joint meetings and present this as a poster, but weren't able to in the end. But there's research being done by many people still on exactly how hyperbolic the curve graph is. Okay, so the summary at this point in the story, it turns out that Gromov hyperbolic spaces are for some purposes very easy to work with. Although I should emphasize that despite being Gromov hyperbolic, the curve graphs are still very mysterious. So we're happy about that. And you want to leverage this to understand other spaces like Teichmüller space or like the mapping class group. And you're happy because there's a map from Teichmüller space to the curve graph, which you would usually call the systole map. It sends any hyperbolic surface to a shortest curve on that hyperbolic surface, a systole, which doesn't have to be unique, but maybe you pick one, and that's fine. And this is a very useful map, and it lets you leverage the negative curvature of the curve graph, the Gromov hyperbolicity, when studying Teichmüller space. And so that's great. The downside, you're sad because that map loses a lot of information, as is illustrated in this picture. So here I have a genus 2 surface with this one curve very, very short in the middle. And what's happening is I have these 2 halves of the surface, U1, U2, the 2 subsurfaces, what you get when you cut the short curve. And you can change U1 and U2 a lot without changing the shortest curve, because it's that curve in the middle. So roughly speaking, you have a whole copy of the Teichmüller space of U1 cross the Teichmüller space of U2 that's mapped to this one curve, this short curve in the center. So this map to the curve graph tells you a lot, but somehow it loses a lot as well. Now, happily, this is a problem with a very good solution, and that's also to make use of the curve graphs of U1 and U2. So for example, the situation would be mitigated if you remembered not just the shortest curve on the whole surface, say it's this one, but then also the shortest curve on U1 and the shortest curve on U2. Then that would tell you something about what's going on in these subsurfaces. And actually, there's a way to use the curve graphs of all the subsurfaces, and I won't provide the details to you now, but you can get a map from Teichmüller space to the product of all curve graphs. So this is an infinite product of graphs, because there's infinitely many subsurfaces, and all of these graphs are very complicated. They're locally infinite, and we don't have a perfect understanding of them. But this turns out to be a very useful map. Raffi, following Mazur-Minsky, who proved it originally for the mapping class group, proved a coarse version of the statement that this is an isometric embedding. So specifically if you use the L1 metric on the product of the curve graphs. So coarse means there's some error, and I won't tell you exactly what that means. But there's something called the distance formula that up to some error lets you compute the distance between 2 points in the curve graph, in Teichmüller space from their images in the infinite product of curve graphs. And then later, Baerstock, Kleiner, Minsky, Mosher gave a very, very simple description of the image. So you don't get the full product of every curve graph. There's some very simple and transparent restrictions, and you know exactly what you get. And the result is that you think of the product of the curve graphs as a sort of coordinate system for Teichmüller space. It's an infinite dimensional coordinate system because there are infinitely many subsurfaces and each coordinate lies in a Gromov hyperbolic space. And it emerged that for many purposes, this is just an overwhelmingly powerful perspective. And to my mind, this is very audacious or shocking you start with a space which is at least homeomorphic to r to the 6g minus 6. So you can parameterize it with some finitely many real numbers. And then you say, no, I don't want to think about that. And in fairness, those are not so useful for geometry. Instead, I'm going to put an infinite coordinate system where I have infinitely many coordinates. Each one lives in a very complicated, locally infinite graph that I don't understand perfectly. But it's emerged that this is just, for some purposes, overwhelmingly powerful, thanks to the power of Gromov hyperbolicity and the subsequent results that were proven. Okay, any questions so far? Okay, so then starting in 2017, there's what you might call the postmodern era, if the Mayer-Minsky machine was the modern era. And this is the era of hierarchical hyperbolicity. This was initiated when Baerstock, Hagen, and Sisto gave axioms for what a metric space, what you'd have to know about a metric space to get a version of all these results. That it would have a sort of nice and useful coordinate system where the coordinates are possibly infinitely many Gromov hyperbolic spaces. This notion, hierarchical hyperbolicity, is very special. It's a very stringent definition. Even if you have a nice space with some negative curvature or non-positive curvature, you shouldn't assume it would be hierarchically hyperbolic. The conditions to be hierarchically hyperbolic are very strict. Very non-generic, but they're very useful if they're satisfied. And the big surprise is that there are a ton of examples across geometry, geometric group theory, hyperbolic three manifolds, many different areas. So I might say that the Mayer-Minsky machine is a gem of 20th century mathematics that helps you understand things like moduli spaces, Teichmüller spaces, mapping class groups, which are some of the central objects in mathematics. And now there are gems everywhere. Just to give you an idea of how many examples now and how much are known, rather than listing facts or examples, I showed you a picture of a workshop at Banff, which is limited in size because Banff can only accept so many people, but already you see there's a lot of people coming up with new examples of hierarchically hyperbolic spaces and proving new facts about them. I wasn't going to list examples, but being in this building, I feel I have to list at least one example since we've all been in that atrium that's very cube-like. So one of the initial examples was cube complexes of hierarchically hyperbolic spaces. Okay. Throughout this whole story, I've been alluding to a metric on Teichmüller space, which I haven't specified. And actually, there's any number of interesting and important metrics on Teichmüller spaces. And the two most important being the Teichmüller metric and the Weil-Petersen metric. And up till now, I've been vague enough and imprecise enough that a version of what I've said applies to both the Teichmüller metric and the Weil-Petersen metric. But I really want to focus on the Teichmüller metric and then get to totally geodesic subvarieties. So what is the Teichmüller metric? Well, before I tell you that, I want to tell you another point of view on Riemann surfaces. So again, Riemann surface is a surface with a complex structure. So it turns out that every point in Teichmüller space, when you view it as not as a hyperbolic surface, but as a Riemann surface, can be presented as a polygon with side identifications. So you're probably familiar with the fact that if you take the square and identify opposite sides, you get a torus. Or if you take an octagon and identify opposite sides, you get a genus 2 surface. But here I want to emphasize that we're doing more than topology. These polygons live in the complex plane. And when you do this gluing, you can get a surface with a complex structure. And you could change the polygon, keeping parallel edges identified, and you wouldn't get the same Riemann surface necessarily. You might get the same topological surface, but with a different complex structure. And I'll say I've chosen to be as elementary as possible for this talk, but generally speaking, you think of these as quadratic differentials on the surface. Okay, so a theorem, or really it's two theorems, Teichmüller's existence theorem and Teichmüller's uniqueness theorem, says that for any pair of distinct points in Teichmüller space, you can find an essentially unique polygonal presentation of 1 and a unique real number t, a positive real number, so that when you stretch out the polygonal presentation, so you stretch it out horizontally and contract it vertically, you get a polygonal presentation for the second surface. So somehow there's a way of specifying the first surface so that when you stretch and contract it, you get the second surface. And here's an illustration where you start with a torus. I haven't drawn side identifications, but it's always implicit. I'm identifying the opposite sides, and I scale it out. And there's some cut and paste here on these polygonal representations, and you get a new surface. And just for fun, I've drawn a vertical segment so you could see it getting shorter as it's contracted by this. And really, this is a theorem, but for this talk, let it be the definition that the Teichmüller distance from x to y is t. So it's how much you have to stretch out a presentation of the surface to get from x to y. So some facts. So first of all, with this definition, it's not obvious it's a metric, but it is a metric. You might ask if the metric is Riemannian. Not quite. A Riemannian metric is determined by an inner product on each tangent space. This metric is determined by a norm on each tangent space, but the norm doesn't come from an inner product. So that's what a Finsler metric is. And the definition I've given you is what I would call very modular. It keeps track of the fact that Teichmüller space is a moduli space. It parametrizes something. So the distance is calculated using the Riemann surfaces that points represent. There's another point of view on the Teichmüller metric where you use the fact that Teichmüller space is not just a real manifold, but also a complex manifold. And any complex manifold, only using its complex structure, has something called the Kobayashi pseudometric. And in this case, the Kobayashi pseudometric is a metric, and it's actually equal to this Teichmüller metric. So you see these two sides of the Teichmüller metric. On the one side, it has this modular meaning in terms of how much you have to stretch out the surface. And on this other side, it has this meaning that's intrinsic to the complex geometry of Teichmüller space, not relying on it being a moduli space. So to elaborate on the previous slide, if you fix a surface and pick one of these polygonal presentations of it, and you apply these matrices e to the t over 2, 0, 0, e to the minus t over 2 for different positive values of t, what you get is a geodesic. And that just follows directly from the definition of distance on the previous slide. So already I would say this is very remarkable, even for Riemannian metrics, and Finsler metrics are worse and more complicated than Riemannian metrics. You typically don't get to know the geodesics. They're the solution to some EDE. You maybe do not feel like you have the right to know exactly what the geodesics are. And this is especially complicated. The space is as asymmetric as possible. It's not even Riemannian. And so it's very remarkable that, at least from one point of view, we can say what the geodesics are. From other points of view, you would have no idea. Like if you wanted to know the geodesics in the real coordinates I mentioned before, where Teichmüller space is r to the 6g minus 6 plus 2n, forget about it. But from this point of view, you know what the geodesics are. But anyways, we could also do other things to the surface. We're talking about just stretching them, just applying this one 2x2 matrix. But you could also rotate or shear the surfaces, or really act by any 2x2 invertible matrix. You could act by all of GL2R. It's just as good to act by SL2R, so let's do that. And you can think about the SL2R orbit of one of these presentations of the surface. Now, to start with, let's think about what happens when you rotate. So when you rotate, you change the presentation, but you don't actually change the complex structure. SO2, the group of rotations, fixes a point. So just by the orbit stabilizer theorem then, you get a map from SL2R mod SO2R to Teichmüller space. And SL2R mod SO2R, that's the hyperbolic plane. So you get a map from the hyperbolic plane to Teichmüller space for each of these presentations. That again, from a certain point of view of these presentations, is very concrete. And it's not hard to show from the definition of the metric that this is an isometric embedding. So you get copies of hyperbolic disks inside Teichmüller space. And these are called Teichmüller disks, or sometimes they're called complex geodesics. I'm very used to calling them Teichmüller disks, so I'll continue to do that. But complex geodesics are a very good name. You should think of them as sort of complexifications of the real geodesics. And in fact, since there's a unique real geodesic through any 2 points that you get by just stretching and contracting a polygonal presentation, just by acting by SL2R, you also get a unique Teichmüller disk through any pair of points. So the philosophy that I might try to sell here is that Teichmüller space is very mysterious, it's asymmetric. We don't have a good understanding of its geometry at a fine level. But we do have this really abundant supply of these hyperbolic planes, these Teichmüller disks in it, which the hyperbolic plane is comparatively very simple. So you use these abundant and comparatively simple Teichmüller disks as a key tool when trying to understand Teichmüller space with the Teichmüller metric. So there's a lot known about Teichmüller disks, but let me tell you one of the deepest and most remarkable results, which is a theorem. It's a paper of Eskin Mirzakhani, and then a paper of Eskin Mirzakhani Mohammadi, and then finally a paper of Philip, that shows that if you take the Teichmüller disk, which lives in Teichmüller space, and you map it to moduli space, so then it starts to wrap around. I'll show you a picture on the next slide, and then take the closure, not in the Zariski topology, but in the analytic topology, you get an algebraic variety. This is a very powerful and deep and difficult theorem. It was cited in the Breakthrough Prize of Alex Eskin and the Fields Medal of Maryam Mirzakhani. And it's sometimes called the magic wand theorem due to the powerful applications it has to billiards in rational polygons and interval exchange transformations and the geometry of Teichmüller space and a surprising array of other problems. And I should say this was very much born out of the comparison to symmetric spaces. On the symmetric space side, you have Ratner's theorems on unipotent flows. And this result derived from the desire to establish a version of those theorems for the moduli space of Riemann surfaces. And actually, the last time I came to the joint meetings, which was a while ago now, I gave a current events bulletin. Just on that one theorem, there's a lot you can say. And a survey from that's called From Rational Billiards to Dynamics on Moduli Space is available on my webpage if you want to know more just about that theorem. So just to give a very simple analogy, a Teichmüller disk in Teichmüller space is a tiny bit like a line in R2 in the plane. And the map from Teichmüller space to moduli space is like the map from the plane R2 to the torus R2 mod Z2. And if you take a typical line in R2, so to be precise, one with irrational slope, and you map it to the torus, it winds around densely. So here I'm drawing the torus as the square with opposite sides identified. And so this gives you an idea of how a simple object in the universal cover can wrap around and have a much bigger closure downstairs. And similarly, actually, most Teichmüller disks map to a dense subset of the moduli space. So the variety produced by the magic wand theorem, when you take the closure, is usually just all of moduli space. So it wouldn't be very interesting if that always happened, but it doesn't always happen. Sometimes the variety is very interesting. This is something that I worked on a lot starting when I was a graduate student, and actually I went to Stanford as a postdoc specifically to work with Mirzakhani on the problem of classifying what sort of closures you can get, what these varieties can look like. And there's a lot known. For the moment, let me just say that there are some interesting examples. So already some examples were known before this, but Mirzakhani had a particular conjecture for what sorts of varieties would exist, and in joint work with Kurt McMullen and Ronen Mukamel, and later also Alex Eskin, we found finally many new varieties that occur as closures of Teichmüller disks that were unexpected in that they violated Mirzakhani's conjecture. Later work has confirmed what I would say the vision behind Mirzakhani's conjecture, that there are very significant restrictions on what the variety can be. These were discovered in relation to Mirzakhani's conjecture, trying to work on her brave vision for what these varieties might look like. And when we found these, we discovered that a few of them were even more amazing than we had thought. They were what's called totally geodesic. And we had never thought to look for something totally geodesic. There was no reason to think that any non-trivial examples existed. But having discovered some of these varieties, we found that 3 of them that were complex surfaces in 3 different moduli spaces had this property. So what is totally geodesic? Well, a complex submanifold of Teichmüller space is totally geodesic if it contains the Teichmüller disk, the complex geodesic, through any pair of its points. And furthermore, you say that this complex submanifold is algebraic if it covers a variety, in which case you call that variety totally geodesic. So in other words, a subvariety of moduli space is algebraic if when you lift it to Teichmüller space and take a component of that lift, it contains the geodesics between any pair of its points. So what we found is that some of these examples, even though we weren't searching for this or hadn't thought that this might be true, some of these examples had this property of being totally geodesic. And you should have in mind that there's some sort of dimension count here. You want to know that there's enough Teichmüller disks in your variety, and then there's a dimension count, what dimension of Teichmüller disks do you have versus what you would need to join every pair of points. And that gives you a little bit of the flavor of what it's like to check that a variety is totally geodesic. Okay, so let's talk more about totally geodesic submanifolds. So right from the definition, you see that the totally geodesic submanifolds of dimension 1, so complex dimension, I'll always refer to complex dimension, are just the Teichmüller disks. Okay, because a Teichmüller disk is already 1 complex dimensional, so that's the whole thing if the manifold's 1-dimensional. Most of these are not algebraic. I've already said most of them project to a dense subset of moduli space. So the ones that are algebraic are a bit like the lines of rational slope on the torus. This is a special thing. Nonetheless, there are some Teichmüller disks that are algebraic. They cover a variety of dimension 1, so an algebraic curve in moduli space. And these are much studied curves called Teichmüller curves. And there are a lot of them. There's infinitely many in each moduli space, in each MGN, so they're abundant. Surprisingly, the situation in higher dimensions, so complex dimension greater than 1, is somewhat opposite of the situation in dimension 1. So first of all totally geodesic submanifolds of dimension greater than 1 are automatically algebraic. So that's as if every line in R2 automatically covered a circle in the torus, or like all lines were automatically rational slope. And furthermore, there aren't so many of them. There are only finitely many in each moduli space. So this is a result that built on previous work of a more dynamical nature that was joint with Alex Eskin and Simeon Philipp. So we have a dichotomy here for totally geodesic submanifolds and varieties that in complex dimension 1, they're abundant and simple. Simple just in that they're hyperbolic spaces or hyperbolic curves. In dimension greater than 1, they're rare. Okay. And furthermore, I'd like to state to you that they seem to be very complicated. Or more precisely, in complex dimension greater than 1, they seem to be as complicated as a whole Teichmüller space. So you might think of these higher dimensional totally geodesic submanifolds as exotic Teichmüller spaces. And moreover, there's, I would propose the meta-conjecture that these totally geodesic submanifolds should have many of the same properties that Teichmüller spaces do. And similarly, the totally geodesic subvarieties should have many of the properties of whole moduli spaces, and the fundamental groups of these subvarieties should have many of the same properties as mapping class groups. So the mapping class group is the fundamental group of the moduli space. Okay. So any questions so far? Yeah? I do not know generators and relations for them. That might be something that you could figure out, since we do have some understanding in the 3 examples that we know about. Any other questions? Yeah? Yeah, some, and that's been started to study. And the few examples we know are connected to classical algebraic geometry and arise via dihedral maps and dihedral forms. And we have, I think, some understanding of them, at least sort of birationally. We can parameterize a dense set. Yeah? Most of the time, if it's a complex submanifold, then it would automatically be an algebraic variety if it had a reasonable structure at infinity, if it didn't have some sort of essential singularity behavior at infinity. Okay, great. So this brings me to the final section of the talk, where I'll mention some new results. This is new joint work that was just posted on the archive in December with Francisco Arana Herrera. And we have 2 main results, and a version of the first result was obtained independently and simultaneously by Fred Bernischker, Ben Dozier, and John Rashed. Okay, so this is the theorem. It's about the boundary of a totally geodesic submanifold in the Deligne-Mumford in the Deligne-Mumford boardification. So the Deligne-Mumford boardification is built out of pieces that each strata that each are product of Teichmüller spaces. So I look one piece at a time. I take a totally geodesic submanifold. I assume it's algebraic, but that's automatic if it's dimension greater than 1. And I look at the intersection of its closure with one stratum of the boardification. So that's something that lives in a product of smaller Teichmüller spaces. Then the theorem is that this piece of the boundary is what we call semi-simple. So I should tell you what semi-simple is. Well, semi-simple, first of all, means it's a product of simple totally geodesic submanifolds. And what's a simple totally geodesic submanifold? Well, n is simple if, when you use the sup metric on the product of Teichmüller spaces, each projection to a coordinate is a isometric embedding. And the image is a totally geodesic submanifold. So I want to elaborate on that, so let me repeat the definition on this phrase. So again, I'm using the sup metric on the product. So that says the sup of the distances in the coordinates given 2 points has to be equal to the distance in any given coordinate. So if you unpack that, what it means is that if you have 2 points, x1 through xk and y1 through yk, so these xi's live in the different Teichmüller spaces. If you're in a boundary where that's a product of k Teichmüller spaces, then it's saying that the distance in the I coordinate is equal to the distance in the j coordinate for any pair I and j. And so this is the metric behavior of a diagonal embedding. So if you look at any metric space and look at its diagonal inside of its product, if you compare the distances in the different coordinates, they'll be equal. So in short, the semi-simplicity result says that each piece of the boundary behaves like a product of simpler pieces, and each simpler piece behaves metrically like a diagonal embedding. Okay, so I want to do what I would call a trivial example. So what do I mean by a trivial example? Well, it turns out totally geodesic subvarieties or submanifolds appear in what you might call commensurability classes. So you could start with one and do some covering stuff and get a bigger one that's sort of just another version. From the point of view of group theory, it's like passing to a finite index subgroup, something like that. So it's not something totally different. So here I'm going to take the Teichmüller space of genus 2 surfaces and disguise it a little bit and get it to be a totally geodesic submanifold of the Teichmüller space of genus 3 surfaces by taking degree 2 covers. So it's trivial in that really it's just a copy of like all of Teichmüller space in genus 2. And it's sort of boring that that's totally geodesic. It's just automatic. This submanifold of the Teichmüller space of genus 3 surface will consist of degree 2 covers of genus 2 surfaces, like the one drawn here. I've drawn a pair of red curves that are exchanged by the deck transformation, the involution. And if you pinch these 2 red curves, what you get is you get 2 blue components that are genus 1 with 1 puncture, and you get 1 tan component that's genus 1 with 2 punctures. And the two blue components are exchanged by the involution, so they're the same. They have the same hyperbolic metric or the same complex structure. So what you get is that you pinch these red curves and you get a component n of the boundary. It looks like the diagonal in T11 cross T11 times some easy to describe submanifold of T12. And so this is how you should think of being semi-simple. It's a product of things, each of which looks like a diagonal. In this case, it's literally a diagonal. So what that theorem is saying is it's saying even these exotic Teichmüller spaces have the same nice behavior that you see for actual Teichmüller spaces, even when you take covering constructions and try to disguise them a tiny bit. Okay, so when you look at this, you say, well, I have 2 blue subsurfaces, but I don't need to keep track of both of them because they're exchanged by the involution. If I know the hyperbolic metric on one, then I automatically know the metric on the other in some perfect, precise sense. If you have 2 subsurfaces, U1, U2, which are like the 2 blue subsurfaces that are exchanged, and they appear in the same simple factor of some boundary component, then you think of them as storing the same information. They're like the 2 blue subsurfaces that are exchanged, and you think of them as equivalent. And if you take one subsurface from each equivalence class, you get a collection of curved graphs, and it turns out that these form a very good coordinate system for the totally geodesic submanifold in the coarse sense of hierarchical hyperbolicity. So you know exactly what subset of this product of curved graphs you get. You have a distance formula, and you get a lot of information. So formally, the theorem is that if you take a totally geodesic submanifold, then it's hierarchically hyperbolic. So this is, first of all, an instance of the meta conjecture that what's true for Teichmüller space should be true for totally geodesic submanifolds. Teichmüller spaces and the mapping class groups are the two original examples of something hierarchically hyperbolic. So this is also true for these subsets. And second of all, I'll say that this is, although it might look like a coarse statement since there's a lot of coarse geometry involved, geometry where you allow some error, this is hiding a good, or encoding a good understanding of which curves you can pinch, how you can pinch them, how the combinatorics look like in the Deligne-Mumford compactification. So it's this marriage between coarse geometry and fine geometry. Okay, so I don't have time to say much about the proof, but let me just say one idea of where some diagonal-like behavior comes from. So on the left, I've drawn a surface, and if you identify opposite sides, turns out you get a genus 2 surface. You shouldn't try to visualize that. You can compute its Euler characteristic if you want to check. And it has these two edges that are so small you can barely see them, where I wrote a tiny epsilon. Forgive me if it's so small you can't read it. And then if you just let that epsilon go to 0, the surface becomes disconnected, and it becomes two tori glued at a point. So this is a flat geometry picture of degenerating a surface, pinching that red curve we had earlier. And maybe inside of L, this presentation would define a Teichmüller disk that stays in L. And so it's intuitive then that as you go to infinity, you get a presentation for this disconnected subsurface, and its SL2R orbit also stays inside the boundary. Now, when you apply, say, e to the t over 2, 0, 0, e to the minus t over 2, that affects both components equally. It stretches them both out by the same factor. So in other words, it moves them both by t in their Teichmüller space. So you get some of this diagonal-like behavior, where to move, you have to move equally in each of the coordinates. So that's a little hint of where you get the diagonal-like or isometric embedding behavior from. So formally, we use results on what's called the what you see is what you get partial compactification due to myself and Maryam Mirzakhani, and later myself and Dawei Chen, and really an interplay of coarse geometry and algebraic geometry and more analytic or dynamical techniques in Teichmüller theory. So just briefly, what's next? There's a lot of things that might be next, but first of all, can we classify the totally geodesic subvarieties of dimension greater than 1? Right now, we only know the 3 examples, except for passing to covers. And they're all complex surfaces, so are there any examples of complex dimension greater than 2? That's a big mystery. And these results are intended to be useful for that problem. The structure of which curves can be pinched and these subsurfaces and the equivalence relation is a tiny bit reminiscent of the structure of a root system. So there's a lot of topology and combinatorics that you can play around with. And second of all, there are many instances of this meta-conjecture to think about. There are many points of view on Teichmüller space and moduli space in the mapping class group. Many different types of mathematicians study them. And so we can think about these objects, the totally geodesic subvarieties and their fundamental groups and the universal covers from all those different perspectives. Okay, thank you very much for your attention.